Oh, yeah, nice. And
You can take this out or walk around or just make it to your height or however you like to do it. And here's your clicker, but I think I need to click on your screen and then you can be able to adjust.
Does it have a laser pointer? That little red
That little
dot?
red, point it to the.
Okay. Okay.
One of these guys. Yep. Oh, wait, I gotta do.
Oh, yeah.
Okay. I'll try it.
Zoom, PowerPoint.
I just want to say hello, Michelle Valentine.
Oh,
Don't say it was me.
Purple?
Well, I think.
Well, actually, it's more of a purple, royal.
Yeah,
blue
it's
sort
just
of
a
thing.
color.
Yeah.
So
Hey,
excited.
Marty, I think, who's it?
He saw you visit, and so he was saying how excited I am to see you today.
Oh.
Marty's actually still on campus, but
Oh, okay.
yeah, yeah.
Oh, awesome. Are you gonna stay for the talk?
Of course.
Okay.
Yeah.
Well, I'm looking forward to, having you.
Let you know that we. But it's nice to interact more. One of the days. Seemed a little dark, but I was sitting in the audience.
With the solar type.
Yeah.
Yeah, whatever. Yeah. I have papers in my door for you. Already, what mic number are you? You're number 4.
Yeah, I noticed it. Two shows at the same time. Right?
Yeah, it's cool. I'll make that announcement.
Thank you.
Let me go grab a copy of it. Oh, okay. Thank you for letting me know.
Yes.
Yeah.
You would think that in my 15 years of doing this, my proofreading
It's always
skills
something.
would
I
be,
get that. So,
my proofreading skills would be better.
so all it is.
Ah,
That ready?
appointed time.
Good afternoon, everyone. It's time to get started. Thank you for coming. Muters, please stay muted, and there'll be questions and answers at the end if you have any questions for our speaker. People in the room, if you have a cell phone, please silence it. I greatly appreciate that, so we don't have any interruptions. Jane Brockman is going to introduce our wonderful speaker for today.
Okay, great. So welcome. Our speaker is James Albury, who is the director of the Kika Silva Planetarium at Santa Fe College. And he grew up in Miami and at the age of, I don't know, 14 or something, started working for the Museum of Science Planetarium. And he stayed there for a number of years as an employee there. So he has an early interest in astronomy. Came to Gainesville in 1988, majored in astronomy, got a BS degree there, and worked for a number of years at other things. And then I think it was in 2009 he got the position at the planetarium. He served as the co-host of Stargazers from 2011 to 2019. And in 2020, he started a new program, which is on YouTube, that is called The Sky Above Us. And he also has served as the president of the Southeastern Planetarium Association, and he's a representative to the International Planetarium Society. And since he's come to this planetarium, he's developed a number of different programs, which I can attest to being really quite wonderful, with his machine that he uses to show you the night sky. And he has, we have a handout here with his current program, and there's also a couple of things on the back table back there. And I do very much encourage you to go to the planetarium. It's good fun. It's really a great program. So, without further, James.
Thank you. So thank you very much for that wonderful introduction. One thing I wanted to point out about my handout, under the picture of the poster for Daughter of the Stars, it says 5 o'clock. It should actually say 7 o'clock, because I always miss one little typo. So I'm trying not to worry too much about my PowerPoint presentation. I've looked at it like a bazillion times, and I'm hoping I didn't misspell anything, but it's all good. So today I'm going to be going over what I've entitled Lives of the Stars. And I was inspired to give the talk that name because when I was 13 years old, I saw a TV series by Carl Sagan called Cosmos. And one of my favorite episodes that he did was Lives of the Stars, is what he entitled it, The Lives of the Stars. So I produced a planetarium show for our astronomy classes at Santa Fe College that go into how we know so much about the stars, because unlike a lot of scientific disciplines, we in astronomy don't have the luxury of being able to actually physically study a sample. Like in geology, you can break a rock apart and you can study it and you can analyze it chemically and so forth. But with a star, they're really far away. How do you go out knowing how much they weigh? How do you know how bright they are? How do you know how hot they are? Well, I will be able to tell you that in this show, and I'm going to try to keep it to under 5 hours. Okay, so it's kind of like astrophysics, but without the fear, or at least not much fear. Okay, so today's agenda. First, I'm going to Twinkle, Twinkle, Little Star is one of my favorite songs when I was growing up because it summarizes basically the basic principles of astronomy. If you remember the song, Twinkle, Twinkle, Little Star, how I wonder what you are, up above the world so high, like a diamond in the sky, and blah, blah, blah. So stars aren't really small, they're very big, and they don't twinkle, although some of them do pulse, and that has to do with as they're getting older, but it's a variable star thing. But how do we know about the stars as we do. So I'll talk about that. And then I have it broken into different chapters: astronomy versus astrology, let there be light, classifying stars, stellar life cycles, and graveyard stars. So without further ado, let's get going. And those of you who are watching on Zoom, you can send questions to the chat. Oh, lights. Ooh, this reminds me of being at work. Okay. Yeah, that's much easier. All right. So astronomy versus astrology. Now, many of you, and growing up and going to college, I would go to Thanksgiving dinner and my relatives would say, "So what are you doing with that astrology degree?" I say, "Well, I'm hoping upon graduation I can do horoscopes in the parking lot." But astronomy and astrology, although they do sound similar, they differ in how information is recorded and utilized. So first, we talk about what is a star. So ancient people didn't know what the stars were. So initially they thought the stars themselves were gods. So astrology is the study of the movements and relative positions of celestial objects as a means of divining information about human affairs and terrestrial events. So when something bad would happen, say for example, a war or a pestilence or some sort of death would happen on a large scale like a pandemic, they would often blame it on Mars, for example, because Mars, if you look at Mars in the sky, all the planets appear to trend from west to east, and they're called wandering stars because every night they are in a slightly different position. So people thought the planets were even more special than the fixed stars because they could move. But every once in a while, a planet would slow down, turn around, and go in the opposite direction. In particular with Mars, Mars would actually get brighter and brighter as it went in the opposite direction. And we call that backwards movement against the background stars retrograde motion. Now, astronomers tried to figure out what was causing it for years, but having a geocentric or Earth-centered solar system made it very complicated because you had to make it looked like a celestial whirligig. You had circles inside circles, and it was a mess. But Copernicus came along and said, well, why don't we just put the sun at the center and have everything go around it in circles at different speeds? And Kepler said, well, yeah, the speeds are also related to how far away they are from the sun, and it's not circles, it's ellipses. And then Isaac Newton came along and said, oh, well, yeah, it's gravity doing all that. So all of that together led us to astronomy, where astronomy is a natural science, and it studies celestial objects and phenomena, and it applies mathematics, physics, and chemistry in order to explain the origin of those objects and phenomena and their evolution. So if anyone asks you, am I an astronomer or am I an astrologer? I'm the latter, not the former. Okay, so the scientific method came along, and with the scientific method, it's a systematic enterprise where you build and organize knowledge based on testable explanations and predictions about the universe. And the word science comes from the word scientia, which means knowledge. So first you make an observation of something strange that's happening in the universe. And that gives you a question. Okay, why is this happening? So you form a hypothesis to try to explain what's happening. So then you do experiments to try to reproduce or answer that question, to test the hypothesis. Then you tell your friends about it, i.e. peers in your discipline. Okay, I did this to explain this. Can you try it and see if you get the same results? And if everybody gets similar results, then you publish your information and it goes out and it's called a theory. So unfortunately, the media has made the term theory sound like it's something that's not proven and not tested, like the Big Bang Theory. Well, that Big Bang, evolution, those things, the reason that they're called theories is because we've actually found evidence of the things that lead up to the solving of that hypothesis. So the scientific term that you give that when you're done, after you've gone through all the experimentation, you've reviewed it by your peers, and everyone agrees on, okay, this sounds like a reasonable, plausible cause for why this is happening, then it's a theory. So if the results are reproducible, that's where you get the theory. So in studying the sun, because we didn't, we saw the stars in the sky, but then eventually people realized, well, the sun must be a star just very, very close to us. So they were able to study the sun, but there's only so much studying you can do with the sun. Okay, the sun is really bright and the sun is really hot. So what are the things in nature are bright and hot? Well, fire is bright and fire is hot. Okay, is the sun made out of fire? Well, things aren't usually made of fire, they're just on fire. So something has to be burning. So they're thinking, okay, well, what things can burn? Campfires are great because they're made out of wood and wood burns. But the only problem is eventually you run out of material to burn and the fire goes out. And the sun has been burning consistently for all of human history and before. So up to that point, thousands of years as people interpreted the age of the universe. So what could the sun possibly be made of that allow it to burn that long? So we had to study the sun in a different way. And that is where chapter 2 comes in. Let there be light. I chose unique names for my slides. Yeah. Okay, so the telescope was the most fundamental advancement in the study of that helped us advance astronomy, just because of the way it was able, as people used the telescope as the years passed, we could gather a lot more information about what was happening in the sky and with stars. So it was originally invented by Hans Lippershey, sometimes pronounced Lippershey. He was Dutch-German, and he was an optician or a glass maker as well. And he had invented the telescope, and he published the information about it in a scientific paper in 1608. And that was originally circulated around Europe. And Paolo Sarpi, he got hold of it, and he sent it to his friend Galileo Galilei. And Galileo was interested in it, so he decided to build his own telescope, and he started looking at the planets, the moon, Venus, and unfortunately the sun. That caused him to go blind in some parts. But anyway, with doing that, he was the first astronomer to use a telescope for astronomical observations. And then Johannes Kepler had heard about all the successes he was having and say, hey, could you build me one of those telescopes? And Galileo replied in a letter, well, I'm too busy to make one and I don't have any more spares. So tough. So Johannes Kepler made his own telescope, and he improved a little bit upon what Galileo had done. And then one of the things about the telescope that Galileo made, those are called refracting telescopes. And you've probably seen one before. It's a traditional telescope where you have this long tube and you have a glass lens on one end and a glass lens on the other end, and the sunlight or whatever, well, not sunlight, you don't want to look at the sun through it unless you have a filter, but the light comes through it and it gets focused on the secondary the eyepiece itself, and then you can see it and oh wow, it looks big and all that stuff. But there's a problem with those telescopes. As they get larger, you have what's called chromatic aberration. Chromatic aberration is where the lenses have trouble focusing the light at all the wavelengths. So at certain wavelengths of light, it will look fuzzy and have a little rainbow color around it. I'll show you an example of that on the next slide. So Isaac Newton, who is quite a brilliant young man, he had developed calculus and a lot of the things that he had done before he was 25 years old. So I tell my son, you can accomplish a lot if you don't have Instagram and TikTok. So anywho, the two things that he did with his reflecting telescope is that it avoided chromatic aberration because it used primarily mirrors, and then also you could make the telescope larger, and with a larger objective opening, you could get fainter light come in and you can see objects that are even further. So, for example, I apologize for this is too tiny. Can you all read the majority of it? Okay, so anyway, the type of telescope that I was talking about earlier is the refracting telescope. It's this one where the light comes in here and it goes up to the eyepiece. They use primarily lenses. The Newtonian reflector bounces light off a curved mirror back here. It's focused on this mirror and then it goes up to the eyepiece. Now the I always mess that up. I've never been able, catadioptric, that's what it is. Okay, the catadioptric telescope uses both lenses and mirrors. And the good thing about this type of telescope is it's much smaller. and it's easier to carry around, like the Schmidt-Cassegrain, for example. I have an example of that, and it's in my office, and it's really small, and I can carry it with me wherever I go, and it does a really good job at magnifying things in the sky. So this is the difference between chromatic aberration and not having chromatic aberration. So that's what we call transverse chromatic aberration, where it's to the side. And this is a picture of Isaac Newton's telescope that he made. So it avoided the chromatic aberration that the refracting telescopes did, because it used mirrors and not lenses to magnify and focus the light. So when studying stars, one of the other things Isaac Newton did was he studied light a lot, and he noticed that when you pass an ordinary beam of light through a prism, which is that triangular piece of glass, you get a spectrum. Now, there are multiple types of spectrums. The one that we're used to, that we're familiar with, is the continuous spectrum. That's what when you go outside and you see a rainbow, that is what's happening. But the spectrum is much larger than what we can see with the visible eye. So the visible spectrum is only a small part of the entire electromagnetic spectrum. And it goes from red to violet. So it's red, orange, yellow, green, blue, indigo, and violet. And the larger wavelengths are over to the right, and the smaller ones are on the left. And you have infrared and radio waves, and you have microwaves over there too. And then you have ultraviolet, X-rays, and gamma rays. These will kill you very quickly. These will kill you slowly in high enough increments, doses, yes. And then visible light, it's annoying if you're trying to be in the dark. Okay, so when people looked at the spectrum of the sun, they noticed that you could actually see more if you were to run it through a diffraction grating. So for example, what we scientists do is we'll take a light source, bounce it off a mirror to what's called a diffraction grating, and it will separate the light even more. And then as it's reflected off a mirror, the mirror spreads the spectrum out so we can see it in more detail. And then we have a detector there to measure that change. And it turns out that when light passes through a gas cloud, some of the elements will absorb some of those wavelengths of light. And I'll explain how that happens later. And if you're burning something, it will actually emit light in those particular same wavelengths of light, depending on what it's made of. So we have a continuous spectrum, an absorption spectrum, and an emission spectrum. And these two are quite important when it came to studying the stars, so we knew what we were looking at. So elemental fingerprints and stellar spectroscopy is what I entitled this slide, because every element has its own chemical fingerprint. So since each element has a characteristic set of absorption and emission lines, by studying the spectrum of a star, we can tell what elements comprise the star. And the absorption lines in the star spectrum can also be used to determine the star's temperature. And I'll explain that as well. So, oops, go back. Go back. There you go. That's Carl, but I'll show them to you later. Okay, so hydrogen has a set of lines. Helium has a set. Lithium, oxygen, carbon, nitrogen, neon. Those are the first elements. I don't have beryllium up there, but those are the initial elements that are involved in the production of energy in a star. So how does all this work? So Carl Sagan was once quoted, it was also in Cosmos, if you want to make an apple pie from scratch, you must first create the universe. Basically, what he was saying is everything in the universe is made of stuff. And the trick is to determine what the stuff is, and hopefully the stuff has properties that will make it identifiably unique. And that is where the fingerprint part comes in. So atomic theory, as people were trying to figure out what all of these materials in the universe were made of, people originally said, oh, well, maybe there are 4 elements, earth, air, fire, and water. It's like, no, you're on the right path, but not close. No, well, not as close as you need to be. So Democritus, he was the one who came up with a concept of the atom, and atom in Greek means uncuttable. So it's the smallest thing you can get. We now know that you can get even smaller than an atom. And then Dalton came along and said, well, the atom is probably made of smaller particles that comprise it. And Niels Bohr, he had a model of the atom that had protons and neutrons and electrons in a particular formation. So the nucleus of the atom had protons and electrons in it, and the protons and neutrons, and the electrons orbited like planets orbiting the sun. And then Mendeleev, who I'm going to show later, he organized all those elements into a periodic table of the elements that helped us classify them. So this is Niels Bohr. I guess quite the handsome man if you're into people from the 1900s. Anyway, so proton and neutron, the proton has a positive charge, neutron has no charge at all, and the electron has a negative charge, and it orbits the nucleus like a planet orbiting the sun, which I thought, wow, that's kind of cool how the microcosm and the macrocosm seem to repeat each other. And the atom is mostly empty space. Just to give you an idea of how small an atom is compared to the macroverse, if you had a table here, say example, one of those tables back there that has the food on it, and you could see the individual atoms in that table, and each atom was, say, the size of a grain of sand, that table from one end to the other would be about 2,000 miles long. Yeah, so atoms are really, really small. There are more atoms in my thumb than there are stars in our galaxy. Yeah, so it's amazing. Alrighty, so Mendeleev was a scientist who said, well, you know, there is a pattern to how these atoms are arranged and how many shells they have and how many atoms they have in their outer shells. So hydrogen has an atomic number of 1, so it has 1 proton and 1 electron. Helium has 2 protons, 2 electrons, and 2 neutrons. Lithium has 3 protons, 3 neutrons, and 3 electrons. And neon has 10, it has 10 protons, 10 neutrons, and 10 electrons. So he said, let's go ahead and put together a periodic table where the groups that go across, they tell you how many electrons are in the outer shell, and going down, it tells you how many shells there are, how many shells it has. So you have groupings like one of my favorite groupings is the noble gases. These are inert, they don't react with anything. And then these guys here, they react with everything, and they're quite violent. And then of course you have chlorine on one side and sodium on the other. These two like to work together, and you get salt and all those wonderful things. Now, the elements in a star, I'm going to be talking about later, but most of them are created in most of these from nickel and zinc going backwards. Those are all created in the normal processes of nuclear fusion in a star. Anything after zinc is produced during a supernova explosion. So how do we classify the stars? So back in the early 1900s, Edward Pickering, he was the director of the Harvard College Observatory. That was before it became Harvard University. And he hired a team of highly skilled women to undertake the laborious task of cataloging the stars in the observatory's huge collection of photographic star plates. So people called them computers back then. Some of Edward Pickering's colleagues used to call those women his harem, which that wouldn't fly today. I don't think it flew back then. But there were several members of that team that were quite noteworthy. Annie Jump Cannon, she was the leader of the team along with Wilhelmina Fleming. Wilhelmina Fleming was the discoverer of the Horsehead Nebula. And then Antonia Maury, she put together an initial cataloging of the stars into their spectral classes. And then Henrietta Swan Leavitt, she studied Cepheid variables, and she was able to determine a standard candle for distances to stars. So she was instrumental in us eventually knowing how far away stars are and how far our galaxies are, and ultimately the shape of our own galaxy. So there is a play that was playing in Ocala, and I don't know if it's going to make it, if it ever came to Gainesville, but I know just before the pandemic, there's a play out there called Silent Sky, and it studies the life of Henrietta Swan Leavitt, and there are characters for Wilhelmina Fleming and Annie Jump Cannon and so forth. So if you ever get a chance to see Silent Sky, because Annie Cannon and Henrietta Swan Leavitt were deaf. So Alrighty, so moving forward. So in the first 5 years, this team of women, they cataloged over 10,000 stars. And then by 1924, Annie Cannon had expanded the catalog to 9 volumes with almost 250,000 stars. So that was an amazing accomplishment. But again, when you don't have the internet to interrupt you, you can get a lot accomplished. So, alrighty. So going back to stellar spectroscopy. So when atoms absorb light, it will excite the electrons depending on what frequency the wavelength of light is, because only certain wavelengths of light will excite electrons and make them want to jump up to another orbital. We call that an excited state. So for example, when this photon comes in, it excites that electron that jumps up to another orbital. That's like Earth changing its orbit from here to Mars's orbit. But then when the electron falls back down, it gives that photon back. So would be absorption, this would be emission. And that's how that absorption and emission spectra works. So with a spectrograph, you can see that. So it's almost like a key fitting into a lock. That's why helium has specific lines, carbon has specific lines. So when we look at a star spectrum, we can actually tell which elements are in the star. So stars that we classified as A, those have the strongest hydrogen lines. So originally the classification, when Antonia Maury was putting it together with Annie Jump Cannon, they started with letter A and worked all their way down to letter O. And they noticed that some of them overlapped, so they eliminated those. But over time, they realized, oh, well, we can actually arrange them in a natural order, and then based on the star's temperature and luminosity, other astronomers are able to put together a diagram to explain where all those stars appeared and why they were in those locations. So for example, the stars that are cooler had a lot more absorption lines, but the ones that were really, really hot didn't have any. That's because the stars that are really hot, they're so hot that the electrons are ionized, the atoms are ionized, so the electrons get stripped away. So there's nothing to absorb the photons. So that is why those don't have absorption lines. But the ones down here are relatively cool. Our star, the sun, is a G class. But stars like Betelgeuse, which are red giants, or red dwarf stars, for example, they all have lots and lots of hydrogen lines. So, and a good mnemonic device for remembering this: O, be a fine girl or guy, depending on who you like, kiss me. So that is that's where that acronym came from, or mnemonic rather. Okay, so shortly after this was done, Cecilia Payne-Gaposchkin, she wrote her dissertation it's called Stellar Atmospheres, and it's one of the most profound dissertations that have been written in the history of astronomy. And it made the connection between the absorption lines and a star's spectrum and the surface temperature for the star. So when Hertzsprung-Russell when Edgenar Hertzsprung and Henry Norris Russell independently, they both put together a chart based on her work as well as the Harvard computers, and they were able to graphically correlate a star's size to its luminosity and its temperature, because a star's luminosity is a function of its size. The bigger the star is, the higher the luminosity would be because of the surface area of the star. So, and that's them. All right, so this is the Hertzsprung-Russell diagram, fairly simplified. The intrinsic brightness is listed on the vertical axis, one being the sun. So the sun is right here. And then the temperature scale goes from hot to cool. And these are where the letters more or less fall: O, B, A, F, G, K, M. So the sun is in the G area and we're at a 1. Now, the majority of the stars in the universe spend most of their lives on the main sequence. And then once they leave the main sequence, they'll go through the different areas. So our sun, for example, is going to go up here into the giant branch, and then it's going to come back around, and then it's going to go into the white dwarf. It won't even stay in the main sequence. It'll just go down to the white dwarf and it'll just cool off, and that'll be the end of the sun. But there are other stars that will actually go up here, and then by the time they get into this region or here, they will explode as a supernova, or they will outgas tremendously and become a white dwarf. White dwarfs are what most stars become when they die, but depending on their mass, they can have rather dramatic remnants left behind. Okay, so stellar life cycle. So here's the part where we get into the astrophysics. I won't go into the scary parts of it, but Dr. Hunter would probably be proud of me. Okay, so Dr. Hunter, he was my astronomy professor in astrophysics. Our final exam in his astrophysics class only had 3 questions. I said, oh my gosh. And one of the questions is we had to derive the Boltzmann-Saha equation. I'm like, Dr. Hunter, really? Why? He said, well, you learned it. You'll be okay. I said, okay. It's like either take the final or take a bullet to the head. Oh, I'll take the final, I guess. Okay, so anywho, the spectral class is measured O through, oops, go back. The spectral class is measured O through M, so it's here. And then we have a sub-classification 0 through 5. So our star is a G25, so for example, so G2, that's the spectral class. 2 means that it's a hot G star. For example, Sirius is A1, so it's a hot A star. Mufrid is a G0, so it's a very hot G star. And then Betelgeuse is a hot M. Proxima Centauri is a cooler M star. And Arcturus is a K2, so it's a hot K star. Now, the luminosity class, the Roman numerals 1 through 5, the 1 is the Roman numeral 1 that is in the giant branch. So these are all the giants. You have supergiants, A1 and 1A and 1B. Then you have the bright giants, which are 2, the giants, which are 3, the subgiants, which are 4. Then you have the main sequence where everybody's hanging out during most of their lives. And then you have the white dwarfs down here. They don't get a number. But the main sequence is the Roman numeral 5. So all those that have a 5, those are on the main sequence, like the Sun and Sirius and Proxima Centauri. Betelgeuse is in the constellation Orion. That's his right shoulder. In Persian, Betelgeuse means armpit. So if you look at the constellation, it's right under his arm. And then Mufrid was one of the stars in Boötes, the herdsman, and Arcturus is also another star in Boötes. Okay, bing. So this is what a star like our sun looks like on the inside. So they start their lives in a nebula, and a nebula is a large collection of gas and dust that's left behind when a previous star dies. So astronomers believe that when the universe first formed, the first stars were enormous. They were hundreds of solar masses in size. So what determines how a star will eventually die is how heavy or how massive it is when it begins its life on the main sequence. And what determines when a star goes on the main sequence is when it starts to fuse hydrogen into helium. Once nuclear fusion begins, that's when you are now on the main sequence. So if your nebula has at least approximately 171 solar masses of material, gravity will start to overcome the internal gas pressure and the nebula will start to collapse on itself. And as it collapses, it will begin to spin, and as it spins, it flattens itself into what we call a protoplanetary disk. So planet formation seems very common in the universe, and in the last 30 years, we've discovered over 5,000 extrasolar planet candidates. And quite a few of them we can actually simulate in the planetarium. Our planetarium software allows us to fly 3-dimensionally to any of the stars in our neighborhood. And if it has planets, we can land on those planets and we can look at what the sky looks like from there. So you'd be surprised when you go to 55 Cancri, for example, which is 40 light years away, the stars of Orion don't line up in his belt anymore. They're kind of shaped like a triangle because the star in the middle is really, really far away. It's like 1,200 light years away, as opposed to the other two that are 800 and 900 light years away. So as the nebula gets smaller, as I mentioned before, it spins faster, becoming a disk. And then 10 million Kelvin, that is the magic temperature for nuclear fusion to begin, and the star begins to shine. Now, one of the things I found out when I was taking astrophysics that was interesting is that when a photon is released during the whole hydrogen to helium fusion, that photon doesn't go straight out into space and head toward Earth. Because of all the turbulence and the density inside the star, it bounces around randomly inside the star before it gets out to the surface, and then it goes off at the speed of light. So a photon produced today in nuclear fusion will not leave the surface of the sun for probably about 1 million years because of its bouncing around. So the sunlight that you're experiencing when you go outside was made by nuclear fusion that happened over 1 million years ago. Every time I think about astronomy, I get an existential crisis. Because like, really? The sunlight that's hitting me now came along long before humanity was even here. I'm like, things to keep you up at night, eh? Okay. And I would tell Dr. Hunter, really? Is that really? He said, yeah, look at the math. If you do the math and you figure out that a photon has to work its way out, sometimes it'll go up, then it'll go back down, and it's trying to get through almost 1 million miles of material. So the sun is about 1 million miles in diameter, so 500,000 miles of wiggling its way randomly. It's like you being in a crowded room of about 15,000 people and trying to get to the exit, but every time you go this way, someone pushes you back another way. So not to belabor that, but that's how that works. Okay, I'm going to summarize nuclear physics in just this one slide. So when a star first shines on the main sequence, it uses a process called the proton-proton chain, where you take 2 hydrogen atoms and they come together to form what's called a deuteron. A deuteron is like, it's not quite a helium atom yet, but it's on the way there. And then another hydrogen atom hits it, it releases a gamma ray, and then it becomes a helion, which is two nuclei, 2 protons and 1 neutron on both of them. Then they get fused together, 2 of the protons go back into the core, and then what's left behind is a helium atom with 2 protons and 2 neutrons. And that process is extremely stable. And what it does is it helps to balance the gravitational collapse of the star. So a star always wants to crush down to nothing. It wants to keep on compressing itself. One of the slogans we used to have in the astronomy department at UF is that gravity always wins. Yeah, gravity always wins. So, but in this case, once you start fusing hydrogen to helium, you stop collapsing. You just sit there and you fuse hydrogen to helium until you eventually develop enough helium at the core that your core is no longer providing pressure, so the core starts to collapse on itself. Now, as something collapses, it usually gets hotter and hotter. So depending on how massive the star is when it enters the main sequence, it'll tell you how far it can go in that process of what we call nucleosynthesis. Stellar nucleosynthesis is where stars, as they go through each of those phases, they make brand new elements. So the sun will eventually do the second one, which is called the triple alpha process. So helium fusion happens when the core gets so hot that the helium atoms get crushed together and they can become beryllium, and then another helium atom hits the beryllium atom and it can become carbon. So then carbon is what's left in the core. So that will eventually build up, but in our sun, our sun is not massive enough to go through the next cycle after that. So the sun will expand into a red giant when it gets to the second phase, the helium fusion process. And it will expand from its current size all the way to almost the orbit of Earth the first time, and then it'll shrink a little bit, and then it'll expand again all the way out to past the orbit of Mars. Betelgeuse, we're looking at Betelgeuse nearing the last stages of its life, and its orbit, its diameter is the size of Jupiter's orbit. And that's quite big. So if we're in our solar system, we'd all be inside of it: Mercury, Venus, Earth, and Mars. So once there's enough carbon in the core, if the star is over a certain mass, if it's over 8 solar masses, it'll start to collapse on itself again, and then the carbon will start to fuse into nitrogen and oxygen using that last process called the CNO cycle, where by capturing random neutrons and photodisintegration, as we call it, it will go from when carbon captures a hydrogen atom, nitrogen will be formed, and it'll release a neutrino and a gamma ray. And then, or sorry, a positron and a gamma ray. Then it will disintegrate. It disintegrates back into carbon 13, and then it grabs another hydrogen and releases energy, and then it becomes nitrogen 14, then it gets hit by another hydrogen atom, and then it becomes oxygen 15, and then it loses another neutrino and another positron during what we call photodisintegration. It becomes nitrogen 15 again. Then when another hydrogen atom hits it along with a helium atom, it goes back into carbon again. So it's a very stable process, and a lot of stars do that once they get to that stage, the next stage of the carbon fusing process. And it can keep on going. It goes from carbon to nitrogen and oxygen. Neon is formed, silicon, magnesium, titanium, all of those elements. So the core itself is no longer fusing hydrogen, but the area above it is still fusing hydrogen. So the inside of a star starts to look like an onion. So the core of the star, even though it's really tiny, it's got all this fusion going on outside the core, the central core. So each stage of the burning process, there's a specific amount of time that physicists estimate that this would take place. So for example, if you're helium burning, you can burn helium for at least 7 million years on minimum. And then if you are a very big star. So if you are a star like Betelgeuse or Antares, you only burned hydrogen for 7 million years, then you started burning helium and you burned it for 500,000 years. Then you reach that point where you have enough carbon that you can start fusing carbon, and that lasts about 600 years. That's where Betelgeuse is today, we believe. And then you burn neon for 1 year, oxygen for 6 months, and then silicon fusion, that only takes 1 day. So what happens with silicon fusion is that the resulting fusion, along with other elements that you get during that process, you make zinc and you make iron, and you also make nickel. Iron is the one that's the problem, because iron is such a stable molecule that you can't compress it into anything else. And after a day of making iron, the core will become so heavy and so dense that it violently collapses on itself, and the whole star freaks out and explodes. And that is when you get all the other heavy elements during that fraction of a second that the star blows itself apart. You have so many random atoms and neutrons and stuff flying around in the star that you get gold and platinum and uranium and praseodymium and all that fun stuff. Some of it has very short half-lives, but some of the stuff has long half-lives. And when you get a new nebula out of that, and that nebula has all these molecules in it, and the nebula comes back together, you get planets. And on those planets, you get life like us. So the very first generation of stars that went through this, there were still no planets and no stars and no life. But now at this point in the universe's history, we have enough material that is heavier than hydrogen and helium that you can actually get complex life. So we're looking right now, when we're looking for planets around other stars, we're looking for stars that are less massive or the same mass as the sun, because those stars are more likely to have stable enough environments that life can form. Because stars like that only can do this for only a few million years, that's not enough time for life to reach any level of complexity. You'll get microorganisms, but you won't get anything as sophisticated as us. So you won't have, like in Star Trek, how the Romulans, their star went supernova. Not to spoil it for any of you, if you're watching any of the movies. Anyway, but your star wouldn't go supernova if you were advanced civilization. It would go supernova long before you could even become a civilization. So either you guys moved there and didn't realize that your star was going to go supernova soon, or yeah. Anyway. Okay, so stellar lifespans. So the lifespan of a star, as I mentioned before, is determined by its birth weight when it entered the main sequence. So low mass stars like the sun, they usually live approximately 10 to 100 billion years, depending on their weight. So some of them, even the ones that are lower mass than that actually should be 0.1, not 0.8. So I apologize for that. But yes, those can live hundreds of billions of years. So there are still some red dwarf or really small stars in our universe that are as old as the universe itself, and they will continue to shine long after we're gone. And 85% of the stars in our galaxy are of that particular mass. So most of the stars in the sky, some that we can see, some that we can't see, they're all the dimmer ones, the smaller low mass stars. Now, once you get to 2 solar masses, between 2 and 8 solar masses, we consider those intermediate mass stars, and they live about 100 million years. Those are kind of like Betelgeuse, some of the other ones that we were talking about earlier. They're about 14% of the population in the galaxy is that. And then you have the high mass stars. Those are 8 solar masses or above. They only last about 10 million years, and they're the ones that go supernova after they have finished producing all of their material. Okay, so chapter 5, I also called it the final chapter, which goes with the title Graveyard Stars. So these are basically stellar remnants. So these are the potential stellar corpses based on solar mass. So here I have it correctly, 0.1, anywhere between 0.1 and 1 solar mass. Now, if you're ever wondering, could Jupiter have become a star? Jupiter would have to be 80 times more massive for it to begin on this particular, to be a brown dwarf. A brown dwarf is a star that has just, it's almost hot enough to shine, but not quite. So Jupiter is even smaller than a brown dwarf, so we just call it a planet. But even though Jupiter does give off more heat than it gets from the sun, it's not to the point where it could have nuclear fusion. So a star like our sun, its result will be a white dwarf. And basically what's going to happen after the sun expands into a red giant, the nuclear processes in the shell, on the outer shell of hydrogen fusion, that will stop and those gases will float off into space, and then the helium fusion will stop because the helium, the shell layer feeds the layer under it. So hydrogen makes the helium that is hot enough that the helium will fuse into carbon that piles up in the core. So the outer gases will start to radiate out into the solar system. So when the sun reaches that point, we will have what they call a planetary nebula. Now, it's not planetary because it forms planets. They call it planetary because the first people who looked at it through telescopes thought that those nebulae were actually planets. But now that our telescopes are better, they know that they're not planets. They're big gas clouds. So the thing that's left at the center that we call a white dwarf is basically just the hot exposed core of the star. So it's all carbon, some oxygen, but mostly carbon. So if you think of the whole diamond in the sky thing, yeah, that's kind of works. White dwarfs are made of what we call degenerate matter. We call it electron degeneracy. That means the core only has carbon in it, but the electron pressure is keeping it from collapsing any further. So 1 teaspoon of a white dwarf would weigh as much as a battleship. A teaspoon of a neutron star, which is the next stage under that, is so tightly compressed that the electrons can't hold it up anymore, but the neutrons can hold it up. The neutron degeneracy pressure, a teaspoon of that would weigh more than the planet Earth. And then a black hole is where you have a star that's over 25 solar masses. Now, Alnilam, Alnitak, and Mintaka, those are the 3 stars that make up Orion's belt. The one on the left, that one's 40 times the mass of the sun. So when it goes, it's a hypergiant, as they call it, and that star is going to become a black hole when it goes supernova. Now, a black hole, basically, the core collapses on itself so much that it completely disappears. And when it gets that dense, its gravity shoots up. So if you're near a black hole, you'll orbit it, but if you get too close, you'll actually go into it. And the escape velocity for the singularity, that's what we call the remnant of the star that's at the center of a black hole, the escape velocity is greater than the speed of light. So light, no radiation at all, can escape from that singularity. So there's a sphere around that singularity that we call the event horizon. Beyond that, we can't tell anything about it. So the way we discovered black holes is because of the effects that it has around things, to the things that are around the black hole. So a lot of black holes have what are called accretion disks, where material starts to orbit it, and as the material falls into the black hole, the tidal forces from the black hole tear apart the atoms at the subatomic level, and you get a lot of X-ray and gamma radiation. So that's how we were able to detect the first black hole, Cygnus X1, back in the 1960s during a rocket flight. They were studying, and they said, there's a big X-ray source, but there's no star that's doing it. What's causing it? And they realized, oh, that's probably a black hole. So yeah, so a lot of kids come to the planetarium asking, will the sun explode? I said, no, it's not going to explode. It's going to expand into a red giant, and the Earth will, well, the oceans will boil away, and then Earth will be inside the sun, but you don't have to worry about that because that's billions of years from now. So I'd be worried more about whether I can pay my taxes next year. Okay, so anywho, and that was my last slide, and that's me. Wow. Okay, so. Oh, thank you very much for the light.
Okay, it's quite a journey. It's great. Thank you very much. Questions? Anybody have any questions to? All right.
Ooh, we're gonna do the Phil Donahue thing.
Thank you. Great talk. What's the coolest thing that's been discovered with the James Webb Telescope?
Ooh, okay. What's the coolest thing that's been found with the James Webb Telescope? Because they're sending in more information quite often. I have to go back and check every once in a while. If you're not familiar, the James Webb Telescope is a telescope they've been wanting to launch for a long time, but because of budget cuts and other things that they had to do, it got kicked further and further in the future. So they finally launched it. Now, in order for the James Webb Telescope to do what it does, they had to position it far away from the Earth because the heat from the sun and also the interference from light from the Earth would affect it, because it's a telescope that uses the infrared band of light. So it needs to be relatively cool and look at things that are pretty dark. And they positioned it what we call a Lagrange point, which is a balance point in our orbit. There are 5 of them that you could put in you put a small object in a planet's orbit, and it will be balanced gravitationally by the Earth and the sun, and it'll ride along with us. So there's one Lagrange point behind us, away from the sun. There's one between us and the sun. There's one 60 degrees ahead of us. There's one 60 degrees behind us, and there's one on the opposite side of the solar system from Earth. So we positioned the James Webb Telescope at Lagrange point 2, which is about 1 million miles behind us when you're looking at the sun. And one of the pictures that impressed me the most was a picture of Uranus. It took a picture of Uranus, and you could see the rings like very clearly. And I think they used some false imaging on it too, but it was also a bright green. So think about infrared photography of objects in space. It makes them look very different than what you see with the visible eye because it can detect subtleties. One of my friends who is in the Marines, when he was in Desert Storm, and he said one of the most remarkable things he experienced was looking at the stars through his infrared goggles. Because the infrared goggles, when you look with your normal eye, you just see maybe a couple thousand stars if you're out in the desert. But if you put on those goggles, you see millions of them. There's so many stars you didn't know that you can't count them. That's on my bucket list of things that I want to do. I want to go out to the desert or on a cruise ship with some IR goggles and look up. But one of the things that they're looking to see with the James Webb Telescope. The further you look through a telescope, the further back in time you're actually looking, because it takes light time to get here. And since James Webb's telescope is one of the most sensitive telescopes that we've devised, because also the telescope is huge. It's bigger than this room. It's very big. It's a large telescope once it was fully unfolded. But it's detecting galaxies nearing the beginning of the galactic formation in the universe. So that's one of the things that we're looking for. I'm going to look up some more stuff. If you grab my business card, send me an email and I'll send you some more stuff. I might make an episode of this guy above us about the James Webb Telescope. I've been wanting to do that for a while. And now it's been up there for a couple of years. That should be fun. Yes, and I have a question from the back. Yes.
Thank you very much. This was fascinating and very understandable
Yay.
presentation.
Thank you.
And I just wanted to tell you that I have really enjoyed visiting your facility on Santa Fe's campus. And if any of you think that this was good, you ought to see this guy perform in his own place.
Well, thank you.
My question, though, is that you're able to show us the sky
Mhm.
at different points in time.
Mhm.
And, you know, you take questions where people can say they'd like to see the sky on their birthday or whatever,
Mhm.
you know, when they were born.
Yes.
So my question is, what is the most common night sky that people have asked for?
Okay. What is the most common night sky people have asked for? One of them was believe it or not, the birth of Jesus. They wanted to see what the Star of Bethlehem was. So now, historically, if you were to go back to December 25th of year zero, that's not Jesus's birthday. Now, the reason that Christmas is celebrated on December 25th is to give the Christians in Rome something to do other than Saturnalia, which was a celebration of the winter solstice, and there was a lot of debauchery and orgies and nasty stuff going on. So they said, well, let's give the early Christians, let's celebrate Jesus' birthday and we'll put it like really close to that so y'all have something to do. Now, if you were to look back historically to about the time when Rome's governors were requiring people to go back to their homes for the census, when Joseph and Mary went back, February, I know it's either 7 BC or 4 BC. I have to check the date specifically, but there was an appulse or a close passage of Jupiter to Regulus, or conjunction is another way of putting it. Regulus is one of the stars in Leo the Lion, and Regulus means little king, which I thought was kind of ironic. They probably chose it that way. But Regulus and Jupiter had a triple conjunction. So Jupiter, as I was mentioning earlier, the planets tend to trend from west to east, but they'll slow down and go backwards, and that's because we're passing the planet. So like when you're in a car and you're going faster than the car next to you, that planet will look like it's going backwards, even though you're both going in the same direction. So it did that twice, so 3 times actually. So it went this way, then it went that way, then it went this way. And historically, that's something that Zoroastrian priests who lived in Iraq and those areas, they would have been inspired to go look for Jesus when they saw that movement of the planets. Because a lot of people say, well, why was it not a comet, for example? Because Giotto, when he painted the Nativity, he had a comet in there. The reason he put the comet in there was because Halley's Comet passed by the year he was painting it, so he wanted to put it in the painting. I'm like, okay, because comets are usually bad news, like the deaths of kings and the deaths of princes. Another thing it could have been was a supernova, but when we looked historically of any recorded supernovae by the Persians, the Greeks, the Maya, nobody recorded a supernova happening during Jesus's lifetime, which was only about 33 years. So the only thing that archaeoastronomers believe it could have been was a conjunction of planets. And in this case, there was a very prominent conjunction of Jupiter with Regulus during that time period. So when I show people the birthday of Christ, I show them that particular conjunction. I can show the planet Jupiter going back and forth. Because in the Gospel of Matthew, when they got there, they said, yeah, we followed your star and it stopped right above where you live. And I think it wasn't like right after he was born. It was a bit after he was born. So he was probably like a year old by the time they got there. But it was, it's kind of interesting when you can look back in time astronomically and try to figure out what's going on. That's what a lot of archaeoastronomers try to do. And if you ever get to listen to Susan Milbreth talk, she's a prominent archaeoastronomer here in the Gainesville area. She often, has she taught a ILR class? Okay. Well, if you ever get a chance to come to the planetarium, we'll do Tales of the Maya Sky. She was instrumental in the research that went into that. They consulted with her.
Yeah,
Yes,
in the
sir.
last spasm of its life, when a dying star becomes a white dwarf,
Mhm.
what is the duration in time from red giant to white dwarf as it collapses, you know?
Okay, what is the time frame from red giant to white dwarf? So for our solar system, the sun, it'll probably go from being red giant to a white dwarf in probably a little under 1 million years, because it's going to, once the shell fusion stops, then all those gases are just going to float off into space and they'll be dispersed by the radiation pressure of the white dwarf. And then we'll just have a really pretty nebula and some gas giant planets, Jupiter, Saturn, Uranus, and Neptune. Then eventually the solar system will get cold and those planets will start to freeze, and that'll be the end. But you never know. Hopefully we will have evolved to do something other than use Instagram and TikTok all day. So we might actually figure out a way to terraform some of the moons of the other planets for a period of time, but that's 5 billion years from now. You realize between the time the dinosaurs died and us, you could reproduce that span of time 80 times before the sun is gone. So we're in good shape. Yeah, so.
You talk about the age of stars, but how do we know the age of stars? And if we were looking for planets that might have life,
Mhm.
might we look at solar systems that are about the same age as our solar system? For primarily, how do we know the age of stars?
Okay, so how do we know the age of the stars? So a lot of our information or supposition on how we calculate that is based on how nuclear physics works. So as we've noticed that, okay, you need this much temperature and this much pressure in order for you to fuse a carbon atom into a nitrogen atom and then an oxygen atom. So in order to have that much temperature and pressure, you need a lot of gravity. So in order to have that much gravity, you have to have a mass of a certain amount. So when the stellar density gets into the billions of kilograms per cubic inch or cubic centimeter, we know that if your star is a certain mass, it will go through that process. So although some of it is supposition, a lot of it is based on mathematics and other theoretical evidence from nuclear physics. So that's why one of the nice things about astronomy, it's a multidisciplinary endeavor, because we involve chemistry, physics, mathematics, astronomy. So we are astronomy, physics. Yeah. So astrophysics. Yeah. So, and also, how do we know the mass of the sun, for example? You can't weigh the sun and put it on a scale, but Newton, when he came up with his universal law of gravitation, he used Kepler's third law of planetary motion, and he was able to derive it. So you can actually derive the mass of the sun based on how long it takes a planet to go around the sun. So Earth, we know the mass of the Earth, so it takes us 365 days to go around. So we can actually calculate the mass of the sun based on Newton's gravitational law. Now the constant G is a little bit iffy. It's not easily predictable. We can make a ballpark guess. So it's not an exact weight, but it's close enough for government work. So. Okay.
Thanks. The Webb telescope has helped astronomy move forward. What might artificial intelligence and quantum computing allow the field to do that they couldn't do before?
Okay. With all of the advances in astronomy and observations, what would artificial intelligence and I guess hypercomputing, those are, yeah, how will they advance the field? Well, one of the things that I know machine learning, one of the things we use machine learning for is so that we can actually use adaptive optics on telescopes where, when you're looking at the stars here, they twinkle. So the light flickers because of an interaction with the atmosphere. So we actually have computer programs now that will eliminate that flickering from the object, and it will look crystal clear as if the telescope was out in space. So I know that at several conferences, they're talking now about how they can use artificial intelligence to improve the way we analyze data. Of course, that has to, in the science on artificial intelligence is still young, but based on previous things and papers that have been submitted, they're able to teach the computer programs ways to analyze the data in a way that's very similar to how graduate students and other professors analyze data. So I'll be looking into that a little bit more. If you grab my business card, I can email you the answer to that question in more detail. But I think it's a very, it's a positive road. I don't want artificial intelligence to get too far into my everyday life. Like although I own a Tesla, I don't have full self-driving on my car. Mine predates autopilot and all that stuff. I'm not quite ready to have it drive me down the street like Kit in Knight Rider. Not yet. But I'm good with driving on my own for now.
Okay, well, thank you very much. And I hope some of you will be able to find your way out to the planetarium, and
Cool.
maybe even in the future, we'll plan
We-
a.
And we have material on the table there if you didn't get a star
Field
map
trip,
or
good.
one of our, yeah, we should, and we'll have a field trip. I think all y'all fit in the planetarium. We have less than 60, don't we?
Yeah,
And then
right,
on
today
Zoom,
do,
we
yeah.
have 16. Hey, everybody on Zoom, even though you can't see me, but hi.
Great. Well, thank you very much.